So I'm Loubna, I'm a research engineer at Hugging Face, and today I'm going to talk about the rise of small models. And together we're going to see how in the past year we've started moving from very large language models that are over 100 billion parameters to models that are actually small and that work. So not your typical GPT-2, but models that you can actually use for some nice use cases. So the first question to answer is why are language models inherently large? So LLM stands for large language models. And are larger models always better? So if you aim for performance, the answer is yes. And this is backed by theory, so basically the scaling laws. And they tell you that when you want to train a language model, you have to decide on the model size. It is going to be 10 billion parameters, or 20B, or up to 100B, or even more. And you also have to decide on your data size. And they tell you that if you scale the parameter count, basically if you make your language model larger, it is going to be better. So this is described by the loss metric here. And as the model size increases, you get a lower loss, and you basically get a better model. So training larger models actually makes sense. And this is what we've seen, for example, in the GPT family of models, how OpenAI went from GPT-1, which was really small, a few hundred million parameters, to GPT-4, which had over 1 trillion parameters. And everyone noticed that in the performance. And obviously, when they decided to train very large models, they knew that it's going to cost more. But something that people neglect is actually the inference cost. When you decide to train a large model, the training cost is going to be one time, and it's going to be very expensive, but also the deployment. The more users you're going to have, and the more they're going to use the model, the more your inference cost is going to increase. So this is why OpenAI is try to optimize their costs by training smaller models. So that was the case of GPT-4o Mini, which gave a good trade-off between performance and the inference cost. This is also the case for open models. There's a lot of hype around large models, which are really good. For example, like DeepSeek R1, which is over 600 billion parameters, and Llama 400B, and also Bloom. So these models are really large, but they're also really good on the benchmark. And when people try them, they were also good. But for example, for DeepSeek R1, unless you have 16 H100s lying around, that's not a model you can really try. It's very large. And DeepSeek knows that. And people know that. They're, OK, I have a new SOTA LLM, but can I really run it locally? So that's usually the catch with these very large LLMs. This is why DeepSeek released with their R1 model some also small models. This is what they called DeepSeek Distill. There's an 8 billion model and up to a 1.5B. So these are models that are easier to deploy locally and also to use. And they have really good performance on English, on multilingual data, but also on math and on code. This is also the case for Llama 3. After Llama 3, which was 400 billion, then they did another series, which is Llama 3.2. And they have some small models like 1 billion parameters and 3 billion parameters. And the small models hype is not just a hype. We actually have today some small models that are really good. And if we take, for example, the performance on MMLU benchmark, this is a benchmark that tests model performance on a wide range of topics, for example, humanities, STEM, and a lot of different subjects. And if we look at, for example, 2022, the only model that had more than 60% score on MMLU was Palm. And this model had over 500 billion parameters. So we needed to have a very large model for it to be able to solve this benchmark. But if we fast forward to 2023, we had a model which was smaller and was also able to get that score, which is Llama 60B. And then a few months after that, we had Llama 2, which was only 30 billion parameters. And if we fast forward to 2024, now we have Phi 3, which is even smaller. I think it's 14 billion parameters, and it can get that score. So we can see that now, as an AI community, we know how to train smaller models better. So today's small models can be like the past year's very large models. And if we go, for example, to the Hugging Face Hub today, you can see the top 2 trending models actually have less than 2 billion parameters. So that's also another testament for the hype around these small models. So what we want is not to just build very large models. We want to build more efficient models that everyone can use and that are still useful. So if you remember the slide about the scaling laws, I said that if we want to get better models, we can just make the models larger. So that's one way to go about it. Or we can also try to make the dataset size larger. So you fix your model size, for example, 7 billion parameters. If you want to make it better, you just need to train on more data. That's like an alternative to just making it larger, 14 billion parameters on the same size of datasets. So that's one way that we're trying to train better models today. And for example, here in this chart, we can see that in March 2022, for example, the Chinchilla model, which was over 60 billion parameters, it was trained on over 1 trillion tokens. So tokens are like words. And 1 year later, Llama, which was a 7 billion parameter model, it was trained on the same dataset size, and it was as performant as the Chinchilla model. So instead of just making the model larger, they took a small model and they trained it longer. And then Llama 3, which is almost the same size as Llama 1, 8 billion parameters, instead of training just on 1 trillion tokens, they trained on 15 trillion tokens. So that's like 15 times the data set, and they got a model that in the end, it's the same size, so the inference cost is gonna be the same for Llama 3 8B and the same for Llama 7B, but the performance is much better for this model because Meta decided to train on a much larger data set. So that's like a common practice for training small models today, is that you kind of have to pay more for training, but then during inference, you have a model that is small, and everyone can use it at a lower inference cost. So here's like a release timeline of models that have between 1 billion parameters and 2 billion parameters. And for example, you can see that after 2024, we started having some 1B models, but their performance was not very good. So they have less than 40 on MMLU. But then after 2024, we started to having more models that are really small and that have a good performance on this benchmark. So this is obviously just one data point, but it's usually correlated with other benchmarks. For example, the models that are above, they also score well on other evaluation tasks. So how do we actually build more efficient models? I showed that we can try to train these models longer. There are also other techniques, like starting from a larger model and trying to do techniques like distillation or pruning. So these are all ways that we have explored sufficiently today to be able to build some really good models. And this is another plot showing that now we have like some small models that do well. For example, Qwen 2.53b is a model that can get a really good score for its size, so it's over 65 on MMLU. And before that, on 2023, we needed to have really large models to get such performance. So that was a brief overview of why we have more small models now and why they work well. And now I'm going to talk about some models that we're training at Hugging Face. They're called SmolLM, and in particular version 2, which was basically a series of 3 models. We had 100 million parameters, 300 million, and 1.7B. And as you can see in this chart, each model size is the best in its category size. And this defines a new Pareto plot for this type of models. And this is the 1.7B, which was our largest model. As you can see here, it surpasses Llama 1B and also Qwen 1.5B on almost all the benchmarks. We also have an instruction-tuned version, which you can use as a chat assistant. And this is the ranking from the LLMs arena, which is kind of the default to leaderboard for knowing if like a chat assistant is good or not. And as you can see, Llama 1B and SmolLM 1.7B are actually between some models which were much larger released last year. This means that we've made a huge leap forward in terms of making large models, making LLMs more efficient. What makes SmolLM 2 different is not just the performance and beating some models in the same category, but the fact that it's fully open. So the reason we decided to train this model is that there were some good 1B models, for example, like Qwen and Llama, but they didn't give the full details on how they were trained. For example, there's no information on the dataset or the training framework. So it was really hard to reproduce it, and we had to start from scratch, building our own pre-training datasets and also pre-training framework. And then we were able to get a model that performs well. And just like with every Hugging Face project, we wanted to release this full recipe for the community to be able to build similar things. So SmolLM 2 is fully open. You can find the data sets. You can also find the paper with all the details about it, as well as the fine-tuning evaluation frameworks in this repository. And everything is released under Apache 2.0. So we trained SmolLM, which was cool, but then people started asking, can we have multimodal versions? And we developed SmolVLM here, in particular developed by Andy, which is having a talk just right after me. So make sure to join him if you want to learn more about VLMs. And SmolVLM is also 2 billion VLM, which is really good. It doesn't consume as much memory as other models, and it performs very well on the vision tasks. We also had another version, SmolVLM 2, which doesn't just support image, but also video. There's even an app called Hugging Snap, where you can use the model locally on your iPhone, and then just show it around and ask it questions, and it can answer you pretty fast. So I showed you how we can train better models and the examples that we developed. But you might be wondering in which use cases are these models actually good? Because it's really hard to just trust the benchmarks. OK, this model is good at MMLU. It can answer questions about history. But I don't care about that for my use case. So here I'm going to show some use cases of people that took these models and deployed them. So the reason we can use small models now is not just because we have models, but also because we have frameworks to use them locally. So for example, we have MLX, MLC, and Llama CPP, and Transformers.js. These are all excellent tools to deploy these models locally. And also, small models consume less memory and have a lower latency. For example, with our 3 model sizes, you can see how the memory consumption changes. And for example, some models can even fit on an iPhone comfortably, all of them, even without quantization. Privacy or security is another reason for using small models. For example, if you send your data to ChatGPT, of course it stores your data, and you shouldn't be surprised if the next version answers that one question better, because maybe it was trained on it. So if you want privacy and security, you should probably go for a local model. And for example, that was a big selling point for Apple Intelligence. So basically, Apple developed a 3B model that can run locally, and it was used in their latest iPhone 16. And the big selling point was that it can run locally, so this enhances privacy and security. Here's some use cases where you can use these models. So for example, SmolLM 2 supports summarization, rewriting, and function calling. So you can get some good generations for these tasks because we included them during the post-training. You can also do text extraction. For example, here it's a startup called NewMind, where they took SmolLM 1.7b and they fine-tuned it on some text extraction data, and they were able to get a really good performance. You can see that the gap between NewExtract 1.5 and Llama 70b is not that large. So if you really want to cut down inference costs, it should be fine to sacrifice a small performance drop for the much decreased inference costs. Another example we deployed using text extraction is for like GitHub issues. You basically have a user who wants to open a has a complaint, and you want it to open a GitHub issue automatically. So here in this demo, you can just put some text about like a complaint that you have about a repository, and then it automatically opens an issue on the repository, respecting the structure. For example, here, you can have a tag saying that this is a bug. You can also specify the urgency level of the issue, and it can also extract a title from your issue. And this is done without any further fine-tuning on top of the model. It uses a technique called structure generation, which forces the model to respect a certain format that you define, in this case, using a JSON template. You can also deploy these models in the browser, so they will run totally locally. For example, here is a demo that uses Transformers.js on the Onyx to run SmolLM 1.7b in the browser. And you can chat with it as an assistant because it was instruction tuned. You can ask it different questions, ask it just generate jokes. No, we don't have a joke here. But yeah, there's you can either use them locally on your laptop or run them in the browser with different frameworks. So for summarization and rewriting, we also developed like a tool on top of Llama CPP called Smol Tools. So it is very easy to use, and you can try to have it, for example, for summarizing emails. We also have a demo where you basically receive an email, it summarizes it for you, and then it can suggest an answer that's like a polite format to answer your email. So now we can go a bit into the details of how we trained SmolLM 2, because it was not just let's take some random data sets and let's train for very long on it. There was a lot of thought we put into the data curation and also the way we trained these models. So I think the main ingredient for getting this performance was the fact that we spent a lot of time on data curation. So we built some really high-quality data sets. For English, for example, a data set called FineWeb.edu. For code, a data set called Stack.edu, and also for math. And then we mixed these data sets together, and we trained the model on 11 trillion tokens. So that took 24 days on 256 H100s. And then to build small VLM, we trained on multimodal data, and we did some post-training to get instruct models that people can chat with. All our datasets are public. You can find them in our Hugging Face collection. And after we did the pre-training part, we wanted to turn the base model into a chat assistant. So we curated a post-training dataset called Smol. So it's basically an SFT dataset of questions and answers. And it covers a wide range of tasks, so just English queries, but also queries for function calling, so that you can use the model for tool call, also for math and for code. So it's pretty diverse. It has over 1 million samples, and we used it to post-train the model. And then we also did the DPO to be able to align the model on a public dataset. This is a chart to show the quality of Smol. For example, if we take a Mistral 7B base model and we post-train on Smol, we get better performance than the original Mistral 7B instructs. All of the details for SmolLM2 are in the paper, which you can find on archive. We go into detail on how we curated each dataset and also how we mixed them. Because you have a math dataset, a code dataset, and an English dataset, you can just mix them randomly. You need to find which ratio to give for each dataset so that your model is good at all the tasks you care about. You want it to be good at code, but not at the expense, for example, of English. So there's some experiments that need to be done in order to find the optimal mixture for these datasets. And then for your training, you need to find like the best learning rate, the best schedule, global batch size, and things like that. So we did some experiments to optimize them. And then after that, for the training, the same goes for like mixing datasets together and how we build Smol. And then for evaluation, it's really important to not just try to overfit on a few benchmarks and try to cover a wide range of benchmarks very early on in the training. So that allows you to really try to cover all the use cases that people care about for this type of models. So that was my talk. Thank you for listening. And if you have any questions, we can do them now. You can also follow us here.